Good morning, everyone. Today, I'm going to be walking through a practice problem involving the model for 7.2, the circular motion model, and we'll be looking at the specific case of going on a ride. I'm mostly going to be talking about how to use the model in general, but we'll also throw a problem in there and see if you guys can do it. So follow along. If you've had any issues with the circular model stuff, I'm hoping to help you out today. Do not hesitate to ask me questions, either in classroom, email, or the Discord. So let's go ahead and take a moment. I don't know if you've ever seen a ride like this. They're pretty common. I haven't been to a ton of theme parks around here, but they had one back where I lived in California. So I'm hoping that they've got one of these around here. So the idea is that, this is you, and you stand here on this wall, and you travel around this circle. Oops. And as you go around this circle, eventually what happens is the floor drops out. So the floor has moved downwards. The floor used to be right here, but now the floor has dropped out. And look, people are still magically sticking to the wall. I'm hoping you've been on a ride like this, or you've seen people on a ride like this. It's an interesting sensation, and it can give you some insight into what's really going on. All right, so let's go ahead and let's take a moment. We're going to examine what's going on here. We're going to try to get a free body diagram for a person. And we'll try to do a little bit of math as well. So let's think about it first. I'm going to redraw this straight from the top. So here's the ride from the top. And we'll go ahead and say that here is a person on that ride, and that the person is traveling, rotating around the circle. Let's do a little bit brighter color in this direction. So the person's traveling around the circle in this direction, and they're sitting there up against the wall. We definitely have circular motion, and because we definitely have circular motion, we know that the net force on this person must be pointing towards the center of this circle. So they'll have a velocity going around the circle this direction, and a net force going into the circle. That is one of the most important things that you need to get from our model is if something is moving in a circular path, the net force on that object must be pointing towards the center of that path. All right, so next. Let's go ahead. I'm going to redraw this, but now I'm going to redraw it from the side. So here is the wall that the person is sitting on, and here is the person. So they're sitting there with their feet up, just like these fine people up here. Now they are traveling towards us. So the actual direction of travel is towards us. And I don't know if I've ever told you this. If you ever want to draw an arrow coming out at you, the way you do it is you draw a circle with another circle inside it. I don't know why, but that's tradition. Well, actually, I do know why, but it's just not worth an explanation. So this person is moving towards us right now, and yes, that's a symbol for towards us. So what would be the free body diagram for this person? Well, they have kind of some forces. They have some forces acting on them. So here's them. They do have some sort of force of gravity acting on them. We'll call this person P. There's got to be something holding them up. There's not a normal force, because a normal force wouldn't be facing up. In fact, a normal force will be facing to the right. The upwards force must be a frictional force. So they're literally, friction is holding them onto the wall. If the person isn't sliding up or down, these two must be balanced. So what's going on with this force? If they're touching a wall, we know there has to be a normal force. Well, let's look back at this picture. This normal force is facing inwards, right? This normal force is facing that way. And this normal force is our unbalanced force. As the person moves around the circle, this normal force will move with them, and it will always be facing towards the center. This is our centripetal force. This is the force that is causing the person to move around in a circle. The wall is pushing on the person in such a way to keep them moving in a circular path. All right. This is the sort of analysis you have to do to use this model. You have to be able to look at the circular path, decide what direction the forces need to be going, give me a free body diagram, decide which of these forces is centripetal. There has to be a centripetal force if an object is moving in a circular path. All right, so let's think about a question I could ask you on this. Here's a good one. So we'll set this up. If this person has a mass of, let's say 65 kilograms, and let's go ahead and say that the mu value for the friction here is equal to 0.4. Find how fast do they have to be moving? How quickly must they be going around in this circle in order to make this happen? Oh, we also got to give a radius. Let's see. That's about 1 height. That's about 2 height. I don't know. What do you say? 12 feet? About 4 meters? Yeah, we'll run with that. Well, we will say that the radius of this circle is 4 meters. How quickly what must be their velocity in order to get around the circle this quickly? So I'll give you a minute. I'll give you a second. Go ahead, pause the video. I'll zoom back out so you can sort of see everything. See what you can figure out. See if you can figure this out on your own right now. And then I'll get the setup going in just a minute. All right, I'm hoping that you had a chance to pause the video, try it out. I'll go through the basic setup, and then after the basic setup, I'll give you a chance to actually calculate everything again. So the basic setup is this, we know that this net force is really just made out of this normal force, right? That's the only unbalanced force acting on this person. And that this this normal force is our centripetal force that's keeping the person going on this circular path. At every point in this path, the normal force is pushing towards the center, and it is what's pushing the person into the center. So the normal force is the only force pushing them to center. Now, we need to figure out this. We want this person to stay stuck to the wall. And if this person is going to be stuck to the wall, that means their frictional force has to balance out with their gravitational force. Well, how big does their frictional force get to be? Their frictional force is as big as mu times their normal force. So that's going to be important. Now, here on this end, I asked for the velocity. So we know that the amount of force required to keep something going in a circle is equal to the mass of that object times its velocity squared divided by the radius of that circle. The radius here is 4 meters. The mass of the person we said was 65 kilograms. But the velocity, we don't know. And the amount of force being applied to this person, we don't know. So that's 2 unknowns. How are we going to work through this? Well, let's look back over here. We know that this is our our centripetal force. So this is just Fn. All right, that's the force causing him to go in a circle. But then here, looking at this, we know that Fn will be equal to the force of friction divided by whatever our coefficient is. And we know the coefficient of friction, so I'm just going to go ahead and throw that in. The force of friction divided by whatever our coefficient of friction is, where our coefficient of friction is 0.4. So the force of friction divided by 0.4. Oh, sorry, let me fix. My math's starting to get a little wonky. There you go. So we know that our force of friction divided by 0.4 will give us the value of our normal force, and we know our normal force is what's keeping us in its circle, so it must be equal to this. Now we still have two unknowns, force of friction and the 0.4. But looking over here, we know that the force of friction has to balance out with the force of gravity. So the force of gravity here, we can figure that one out. We know that the force of friction plus the force of gravity has to balance, so they must be the same size as each other. And we can figure out how big force of gravity is. It's not too bad. We know that the force of gravity will just be the 65 kilograms times 10 newtons for every kilogram. So that's 650 newtons. So I'm just going to go ahead and throw this back here, that the force of friction has to balance out with 650 newtons. So 650 newtons divided by 0.4, that's our value of mu, will be equal to 65 kilograms times the velocity squared divided by 4 meters. So I'm just going to move a few things around. I'm going to put this 4 up here, then I'm going to cancel out the 4 and deal with all that. And look, 65, 65, we can do a lot of cheating here. It's just kind of nice. So 4 meters over 0.4 times 650 newtons will be equal to 65 kilograms times v squared. This 650 is just 65 times 10, right? So if I cancel out the 65, I'm just left with the 10. This 0.4 is just 4 divided by 10. So if I do the 4, we keep the divided by 10. Here, let's think of it this way. 4 times 0.1. The 4 balances out, so we just have over 0.1. So we end up with 10 over 0.1. How many times does 0.1 go into 10? 100. So 100 newtons. Oh, actually, we've canceled out a bunch of 100 meters squared per second squared. That's what the units will all work out to over here. It's going to be equal to our velocity squared. And again, that's just me rearranging this and canceling out a bunch of numbers. Well, this is pretty easy. Let's just take a square root of both sides. What's the square root of 100? 10. 10 meters per second is equal to our velocity. So in order to get this person to actually stay up on the wall, we have to move with a velocity of 10 meters per second. So hopefully you were able to follow along with that. Hopefully you were able to see how we applied our model to that. Remember, the trickiest part of this is not the math. I think mathematically this is actually not too bad. You're just solving for all this stuff. Okay, the numbers wise, it's not like 7.1 where you have to switch back and forth between equations, right? We're not doing that. The hard part here is recognizing the relationship between this circular path and the value of this normal force. How do these things have to be related? What goes into our equation right here? That is the hard part here. And then seeing how this is all related to the friction. All right. We'll cut it off for right now, but please do let me know if you have any questions on this. I'd love to go through a problem like this for you. I'd love to help you out. Hit me up on Discord or call me on Classroom, on email. I'll gladly work through something in a voice problem or something like that. Have a nice day, everyone.